Hello everyone, welcome to module number 1, Statistical Concepts, presented by CUSUM. My name is Andrew and I will be your instructor. So, just so you know, this is going to be a Minitab focused training module. We'll be going step by step on some examples. So, first things first, CUSUM as a company is focused on specialized training. This is part of the quality engineer and manufacturing engineering curriculum. So it's focused on new engineers, interns, students that are interested in becoming experts on Minitab. So the following training module has been created in order to train people on how to use Minitab. It is intended to be used as a guide for the analysis of data and self-taught training. If you have any questions, feel free to reach us out at info@cusum.mx. Now, just to clarify, and that's why we have that note over there, the training is hands-on and it's pretty short and to the point. That is our methodology. So you won't be seeing any advanced formulas or any calculations on the slides. We're just going to be focusing on Minitab and how you can use it to run your studies. Okay? Good. Now, we're going to be going through the basic course contents for this module. This is module number 1. So we'll be doing a little bit of intro to statistics, a little bit of basic concepts. What is variable data? What is attribute data? If you already know those concepts, don't worry. We'll just breeze through them. It will be less than 5 minutes, okay? Now, we'll be talking about data distributions. What is normal data? What is non-normal data? We'll be understanding probability and distributions using random data. So what does a Weibull distribution look like? What does a chi-square distribution look like? And why should you care, right? Okay, so we'll also be talking about understanding basic characteristics of data. What's the mean of the data, the quartiles, max, minimum, distributions. These are all very basic things that you see, but you need to actually understand them. If you want to ace an engineering interview, you need to actually know what you're talking about. So we'll be going through that a little bit. And remember, the focus of this training is to turn you into an expert. But you're not going to be an expert from day 1 to the next day. It will be a long, ongoing process. So your main goal right now is just to pass the interview. Okay? You need to know how to use Minitab. You need to know how to analyze your process. And you need to be able to draw conclusions that are statistically valid for that process. You don't know how many engineers I've met who don't actually know what they're analyzing. So that's the focus of module number 1. Okay? We'll also be talking about using Minitab. As you know, there's Minitab 16, 17, and 18. The difference is mainly on the assistant. We'll talk about that a little bit. But don't worry, if you have an older Minitab, you should be able to follow along just as well, okay? Now, we'll also be talking about executing basic statistical tests, which are called normality tests and hypothesis tests, as well as creating graphs, okay? So your normal basic graphs, boxplot, histograms, interval plots, we'll be reaching to those ones, okay? So, going forward and understanding statistics, for your basic textbook purposes, statistics is the science of collecting and analyzing numerical numbers. That's what you're going to find pretty much in every single statistical book. Now, for our purposes, it's just the science of analyzing random data. That's pretty much it. So it allows us to understand randomness and create a structure around it. Even if something is abnormal and you look at it and you say, hey, why does this keep happening on my manufacturing process? Or why does it take so long to measure one part? There's always going to be a trend that you can analyze. Doesn't matter if it looks normal or not normal, there will still be data that you can measure and you can use to draw a valid statistical analysis from. Okay? Good. Now, statistics as a whole is divided in 2 main areas. There's data that is simply random measurements or pieces of information that we currently have. Okay? And it's divided between variable data and attribute data. This is pretty basic. Variable data is simply data that you can measure continuously, and attribute data is data that can only have one state or another. So we'll be talking about a few examples, okay? So variable data is something that you can measure. For example, a person's height. If someone is 7 feet, there can be another person that is 6 feet, another person that is 6.5, 6.9. So there can be multiple infinitesimal divisions between the measurements. Okay, so for example, if baking takes 25 seconds and then 30 seconds and 35 seconds, those are measurements that you can actually quantify with a number. Okay, on the other hand, attribute data is data that you can't actually measure directly. For example, the color of something. The color of an apple is red or green or yellow, but you don't actually have a scale. Unless, of course, you have a spectrometer. But most of us don't actually have one. So that's why color is usually considered an attribute data. If you could quantify color, for example, in an RGB scale, well, at that point, you could actually use it as a variable. But most of the time, you're just going to have it as an attribute. Okay? So in summary, time, weight are variable data, and smells, emotions, colors, those are attribute data. Okay, good. Now we've just gone through pretty much statistics 101 with that. So we'll be going into harder things now. Now, what you need to know is what is normal when we're talking about data. You know, this is kind of a philosophical question, but for statistical purposes, normal means that it can be predicted. We can actually understand when something is normal. So normal data is data that follows a common pattern seen in nature called the bell curve. The bell curve is a statistical concept that tells us how things tend to group up. So we're going to do an example right now so you can understand the difference between normal distributions and non-normal distributions. So we're going to look at an example right now. Let's assume that someone, let's call him Tim. Tim is 1.8 meters tall. I know you're used to using feet, but we're going to be using meters, international metric system, okay? Good. So he's 1.8. And let's say we create a graph. This is called a histogram graph. It divides the values in special categories along the length. So as you can see, it says 1.8. If we looked at this, we would say, hey, everyone is at least 1.7 meters tall, right? We have one data point, it looks perfect, everything is around 1.8, so pretty much everyone is really tall. But that's not true. If I go around and I ask someone else, let's say Clarissa and Marta, Clarissa is 1.6 meters and Marta is 1.55 meters. So I add them up to our chart. And as you can see, I now have, instead of one graph, I already have 3 bars. And well, it looks a little bit odd. The 3 bars are around 1.5 to 1.8, so maybe I can say that people is around that size. But let's say I go around and I ask more people. I ask Thomas, Robert, Ricardo, Pedro, Andres, Gabriela, Mariela, Diana, Maritza, Carlos. I ask them all their heights. And I take all that data and I add it to our graph, or histogram graph. So all of a sudden, I start to see that the data starts to have a certain aspect. As you can see, it's around 1.55, which is around right here. There's starting to be a bigger graph, and all the people are around this size. So I don't have anyone over here. Apparently nobody is less than 1 meter tall, but I'm starting to see that there seems to be a consensus between how tall my friends are. Let's say I had another 10 people. Pablo, Raul, Carmen, Sofia, Tristan, Jackie, Monica, Mercedes, Crystal, and Katia. So I add them all around and add them to our graph, and this is the original one, and this is with another 10 people. Now I have 22 data points. As you can see, I start to have a certain bell-like curve. Okay, so there's a curve that goes around the data, and let's say I add another more people. So I got another 10 more people, so I now have 32 people. And when I add them all together, I get this weird shape, which is known as a bell curve. In statistics, you will most likely find that people say, oh, let's just grab 32 samples, right? We'll be talking about on module number 2 why does sample size matter and why 32 might not be the perfect number. But if you look at the data from where we started with only one person, and you compare it to the data that now we have with 32 samples, we can see that 32 actually lets us know kind of where our population is. So if I go around asking more people, I know that they'll still fall between this area. So that is what's called our bell curve. We're going to do some examples on Minitab right now. This is, like I said, this is a hands-on training. So we're going to be opening up Minitab right now. I'm going to be walking you through the screen, and the slides will also be available here in case. Okay, so we're in Minitab now. So as you can see on your Minitab screen, it looks just like an Excel sheet. You have a menu on the top section where you have all your options. You have this space right here where it says session. This is known as the Minitab session window. We'll be using it later on. And you also have your worksheet window. So this worksheet window works just like Excel. You can type in here information that you want, and it allows you to record information and numbers, as well as dates and text. Now, if you look at it right here, the information that I type in on the first line, this is going to be the column name. So as you can see, column C1 is called type, column C2 is called information, column C3 is called quantity. You'll see why this is important in a little bit. Now, if I type in a letter, the column will change to C1T. T means for text. So if I type in text here, it will also change to a T. Now, if I have a column, for example, the quantity column, and I'm typing in numbers, and for some reason I make a mistake and I type in a letter, it will tell me that there's an error because it's not a valid numerical value. So this helps you out so that you don't make any mistakes while you're recording information. However, please note that if you're trying to record numbers, and at the top it has a T, it means Minitab is treating it as text. Okay, so now we're just going to delete all this information right here. We're going to select it by clicking and dragging on the top row where it says C1, C2, and C3. We'll right click and then we'll select delete cells just so we can have everything empty. Now, in order for us to continue on our training module, there's something you need to learn first, which is how to create random data so that we can use it on our training exercises. So what is random data? It's simply data that Minitab will create for us so that we can graph it, we can create formulas from it, we can analyze it, see how it works. So in order to create it, it's pretty simple. You go over to Calc, which stands for calculations. You go to random data, and you will have all the different distributions that exist for Minitab. Now, the most used is the normal distribution. Okay, this is the most used distribution in statistics. But when we start talking about non-normal data, we're talking about all the other distributions that exist. So just note, normal is not the only option. It's the most used option, and the one that occurs normally, as the name implies, in nature. But sometimes other distributions also exist. We'll talk a little bit about that later on. But first, we're going to be clicking on the normal option, and once you click on it, you'll find that this is your first screen. It's telling you, okay, you want to create normal data with a normal distribution. How many rows of data do you want to generate? Which implies how many different numbers do you want. So for example, right now, I just want pretty basic. I want 100 numbers. Okay? And I want to store this information. Where do I want to store it? Well, I'll just type in C1, right? I'll leave this how it is, a mean of 0 and a standard deviation of 1, and I'll just click on OK. Now, as you can see, data right here has appeared with a total of 100 different data points. I have minimums and maximums. We'll talk a little bit about why a data distribution have minimums and maximums later on. But for now, let's just say this is normal 100. Okay? So this is our first normal 100 numbers that we have created. And let's say we're going to do it a little bit longer. We're going to do calculations, random data, and we're going to click on normal again. This time we're going to use 1000 numbers, and we're going to store the information on C2. We'll keep the same mean and the same standard deviation, and we'll click on OK. Now let's type in a name. We'll put in normal 1000 numbers. Okay, so I can go down, and you can see that I have a lot of random numbers, so I'm not even going to go to the end of it. Okay, now let's say I want to create another normal one that has 10,000 numbers. And I'll just go to Calc, Random Data, and I'll click on Normal. I'll type in C3, and I'll click on OK. Note that I have used the same mean and the same standard deviation, which I know our concepts might not be that familiar to you, or you might not understand as well. But just note that I have used the same setup for each row of data. I have just asked Minitab to create more numbers. That is all. So the first thing that we're going to do right now, so you can start to visualize how data impacts our analysis, we're going to create a simple histogram with this information. So what we're going to do is we're going to go Graph, and then we're going to click on Histogram. Once we click on that, we'll find this menu. This menu has 4 different options. For now, we're just going to be clicking on the simple one. Okay, then we'll click on OK, and it will ask us, what do you want me to graph? So just as you can see right here, you can either double click on this, or you can click on it once and then click on select, and that will select it for you. Now we're not going to be playing around with the options yet, but we're just going to click on OK. And as you can see, this data has the exact same bell curve that we were talking about. But due to the fact that it was created randomly, even though I gave it a mean of 0, this data seems to be going toward the left. Okay, so note, it is bell-shaped, but it's toward the left. Now, I'm going to be adding a reference line just for you. So you can right-click, and go to Add, and then there's an option called Reference Lines. Click on it once, and then type in 0 on the Y value. Okay. Oh, that was actually my bad. That I added it on the Y value was on this axis. So we're gonna do the same thing. Right click, add. We're gonna go to Reference Lines, and we're gonna put it on the data value, which will be the X axis, which is this one right here. Now we'll click on OK. As you can see, there's this line right here. This is the middle point of the data that we created randomly. Now, we're going to be repeating our command right now, where we go to Graph, Histogram, click on OK, and then this time we're going to be selecting the second option, C2, and then we'll click on OK. Now our data starts to have a more distinct bell-shaped curve. Note that this one right here, while it did have the steps, I had this issue right here where this one was actually taller than this one, so it was not a perfect curve. Now on this side, you can see that these ones are smaller than this ones, and then they start to getting larger and larger and larger as they go to the top. And I can see that my middle point, which is 0, tends to be the tallest of them all. I can add a reference line as well to this one by right-clicking, adding reference line, and putting on data value 0. Now note how this middle portion tends to be taller, while before it was taller to be at around -1 or -0.5 instead of 0. Note the difference that 1000 data points has against only 100. Before, you would have thought that this data came from a process that had a mean or an average data point around -1, while now you know the -1 is not even close to the most popular number for your manufacturing process. Most popular number is around 0. So we're going to repeat this one last time with 10,000 data points. We're going to click on OK. And as you can see right here, where before we knew that -1 tended to be really tall, now we know that the main point is around 0, from 0.8 to -0.8. And our data gets, once again, the distinct bell-shaped curve. If I repeat this process and I say normal 1 million data points, and I go to calculations, random data, normal, and I say 1 million data points and stored on C4, I can go to graph, histogram, use a simple one, and run the same analysis. And now you can see the perfect bell-shaped curve that we were talking about. So this tends to happen on nature all the time. But there's another type of data distribution that also tends to happen a lot. And this one is pretty interesting. It's called Weevil distribution. So we're going to be creating a Weevil distribution with 10,000 data points just for you. So we're going to go to calc, random data, and then we're going to go to Weevil, which is the last one right here. Click on it and ask it to generate 10,000 data points. Store them on the Weevil column, and it will tell you, hey, what's the shape parameter and the scale parameter? For now, don't worry about the difference, but let's just put 2, and we're going to put a 4 on the scale. Click on OK. And then we're going to click on Graph, Histogram, Simple. We're going to delete this here, and we're going to put the Weevil one. We're going to click on OK. And note what has happened to the data. The data tends to be toward the left, but there are a lot of data points that fall further toward the right. Why is this? Well, let's do another Weevil distribution, but this time let's use 1 million data points. We're going to be using the same settings that we used for the previous Weevil. We're just going to be storing it on the 1 million, and we're going to ask Minitab for 1 million data points. Okay. Now I'll click on Graph, Histogram, Simple. We're going to grab our 1 million data points. Okay. Now compare this to what we knew of the normal distribution. Our normal distribution is a perfect bell-shaped curve. Our Weevil distribution seems to be bell-shaped, but there are a lot of data points that fall toward the right. This Weevil distribution is pretty common in electronics. If you think about an electronic phone or a laptop or pretty much any electronic device, most devices will fail within the first years of use. However, an important number of them will still be alive and kicking 10 years or later. We've all had the experience of having that one little cell phone that just won't break. Well, pretty much everyone else has had the same cell phone break on them. So, the Weevil distribution, when you are analyzing failure modes, pretty much on electronics, you will find that your data is not normal and actually follows a Weevil distribution. This is what's known as normal data, and this is what's known as non-normal data. Now, why do we care if it's normal or not normal if at the same time we can still graph it? Well, the analysis that you need to execute as a quality or manufacturing engineer depends entirely on the type of data that you're working on. If, for example, you go to Stat, you will see that you will have basic statistics, regression, ANOVA, DOEs, control charts, quality tools, reliability tools. But for example, if you go to quality tools, you will have normal and non-normal. Pretty much in every single analysis that you want to execute here inside Minitab, if your data is not normal, you need to use a different tool. And that is why you need to know the difference. It's not that non-normal data is scary or can't be worked with. It's just that failure modes and capability for a process that is stable toward the middle is a lot more different than analyzing the stability of a process that is skewed toward the left or skewed toward the right. Okay? Now, I hope it didn't confuse you that much. We're going to be talking about this later on in different modules, but it's important for you to understand it. Now, if I gave you two random pieces of information, we're going to be using a chi-squared and we're going to be using normal. So for this chi-square, we're going to type in 10,000. Okay, we're going to be creating 10,000 random data that have a chi-square distribution. And we're also going to be creating 10,000 data points that have a normal distribution. I'll just add ref 2. Please note that in Minitab you can have the same name on different columns. So for example, this one right here has the same name as this one right here. So I can't actually name them the same. I need to put in something different. That's why I'm adding the ref 2 or revision number 2. Now, let's create our random data. We'll click on Calc, Random Data, and this time we're going to be using the chi-square. We're going to type in 10,000 data points. We're going to store them on the chi-square column, and it will ask us for degrees of freedom. Now, don't worry about this concept. It's pretty basic, but for now we're just going to type in 5. Now, we'll click on OK, and we'll have our data. We're going to repeat this for the normal distribution, so we're going to click on Calculate, Random Data, Normal. Then this time, we're going to keep 0 and 1. Okay. Oh, that was my mistake. I did it with 1 million data points, so I'll just repeat that right now. Normal, 10,000, ref 2. Calculate random data, normal. Then we're going to type in 10,000. Yeah, that was my mistake. Didn't notice that. Okay. So I have 10,000 chi-square numbers and 10,000 normal numbers. As you can see, the data is not exactly the same. But what we're going to do right now is run a very simple statistical test, which is called a normality test. A normality test allows you to know if your data is normal or not normal. And using this information, you can analyze it with the appropriate tool. This is going to be your most basic concept which you need to know. You, as a quality engineer or as a manufacturing engineer, must not use a normal analysis for non-normal data or a non-normal analysis for normal data. You need to find out if it is normal or not, and if it's not, you need to find out what it is. So, we're going to go to Stat. There's going to be basic statistics, and right here at the bottom there's a normality test. So click on your normality test, and it will tell you what variable do you want me to test. So this time let's test the normal distribution, and we're going to keep all the settings the same. We're going to click on OK, and as you can see right here, my data seems to follow this line right here. Each individual data point is this red dot that is following the blue line. Note that at the very end, my data became odd for Minitab and stopped following the blue line. This can happen when you're creating random data because ultimately it is pretty much random. Minitab data will try and follow the mean and the standard distribution that you gave it, but ultimately it is random data. And if it might not be completely normal, that's why you will have these data points that don't seem to follow the same line that all the other data points follow. But compare this with our chi-square analysis. We're going to click on Stat, Basic, Normality Test. I'm going to click on chi-square and click on OK. See the difference? Most data right here follows the blue line, while this one is odd shaped. It seems to have a mind of its own, kind of like a banana. And note that Minitab has a statistical value that allows us to know whether or not the data is normal. Right here, there's something called the p-value. Okay, it's just right here, p-value. If this value is greater than 0.05, it means that your data is normal. On the other hand, if your data has a p-value that is less than 0.05, it is non-normal. Okay? Now note I said 0.05, and here it says 0.005. That is 10 times less than the minimum to know if it's normal or not normal. So Minitab is pretty much saying this is nowhere even close. Okay? Well, here the data is 0.187. 187. So that is greater than 0.05. So we can adequately conclude that this data is normal. Now note that the p-value goes from 0 to 1. 1 meaning it's normal. It means it's perfectly normal and there is nothing odd to it, which you will most likely not find. You will usually find values between 0.1, 0.2, 0.5, but it's really rare for you to find a value around 1 on a normality test. Now, on the other hand, if your data is not normal, you can look at it, and you can also analyze it by looking at it. If you see this right here, you can say immediately, without even looking at the p-value, that this data is not normal. However, if we run the same analysis for our Weeble data, the normality test, we're going to grab the 10,000 Weeble data points. Note, don't grab the 1 million because otherwise it will lag. You can see the exact same thing. The Weeble distribution is also odd-shaped. It has a lot more data points following the central blue line, but note that even if it seems to have a bell-shaped curve, it's toward the left. So remember from our data point, for the Weeble histogram, we saw that the data tend to go toward the left. And this is what our graph is showing us. It's telling us that our data is not normal. Now, I hope you have understood what normal data and non-normal data is. We're going to be going back to the slides right now. Okay. And the slides, as you can see right here, they tell you step by step how to create random data and how to graph it using a histogram. What does the data tend to look like? And how to execute a normality test. Now, as you can see right here from just what we talked about, if you see this graph and it follows the red line, you can say that this data is normal. And if you look at this p-value, it's 0.539, 539. That's a lot bigger than 0.05. So you can be completely confident that this data is normal. Now, on the other hand, non-normal data, as you can see, even if it seems to have the bell-shaped curve, there are a lot of data points that just go on and on toward the right. So that's why it's not centered. Now, if you look at the graph, once again, it has an odd-shaped curve, kind of like a banana, and it doesn't follow the red line. Now, there's a word of caution. Normal data can be analyzed using Minitab's built-in functions. Non-normal data can also be analyzed. However, you must take care to avoid incorrect conclusions. So, always look at the graph, look at your p-value, and make sure that the p-value actually makes sense with what you're looking in the graph. If you see a graph that follows the red line perfectly, but Minitab is telling you that it's not normal, you need to understand why and investigate. Now, we'll talk about that later on once we talk about distributions and individual distributions and how to make Minitab tell you if it's a Weeble or a chi-square or what distribution. As far as the testing that we've done until this point, we just know if it is normal or not normal. Now, if your data is normal, it will have a mean, which is going to be the average of all your data. It will have a standard deviation, which is how much each data point separates from the average, and it will have a maximum and a minimum value. Now, standard deviation is the key in understanding statistics. Standard deviation in conjunction with the mean can tell you a lot of information about your process, and you need to understand why it is so important. So now, what we're going to do is we're going to be using Minitab to quickly figure out what is our process mean, which is the average of all our data, what is our standard deviation, which is how much each data point separates from the average, and what is our maximum and our minimum values. So Minitab has several built-in functions. We're going to head over to Minitab right now. And if you go over to Stat Basic Statistics, you'll find two main options. One is Display Descriptive Statistics, and the other one is Store Descriptive Statistics. The main difference between one and the other is that Display Descriptive Statistics will only give you the information in the Minitab session window, while Store Descriptive Statistics will actually store your information in your worksheet. So let's look at an example right now. Let's say you're looking at a manufacturing process called Normal 100, okay? And the first thing you want to know is, what is my process average? What is my minimum value? What is my maximum value? How much does each value differ from one another, which is my standard deviation? And what usually happens is engineers like to copy this information over, they take it over to Excel, paste it, and then they just start saying, okay, average for this, minimum, maximum, standard deviation. Okay, and they say average for this right here, and then they need to scroll all the way down. Say, okay, this is going to be average for this. Then they say, what's the minimum value? Okay, I'm gonna type in just 999 to make it faster. Then they say, what is my maximum value? From B3 over to B999. And they say, okay, and what is my standard deviation? Okay. Now note, this is not an Excel training exercise, but you'll have a standard deviation for the population and a standard deviation for the samples. So the main difference is if you're confident that you took enough samples that this can be considered your population, you can use standard deviation population. If you took a few samples, you're not confident, let's say your production run is about 1 million parts and you only measured about 100 or 1,000 of them, then you would need to use standard deviation sample. So we're going to be using that one. I'm going to put B3 over B999. There we go. Okay. So as you can see, I took about 1 minute, 2 minutes to do this. Well, Minitab can do it for me. So I can go back and I can immediately just go to Stat, Basic, Display Descriptive Statistics, and say, okay, for the Normal 100, I want to know the following statistics. I want to know the process mean, which is the average. I want to know the standard deviation. I would like to know what is the minimum and maximum value. So I'm going to keep this ones here. And I would like to know how many numbers I have. So how many data points I took. I'll just click on OK and click on OK again. And that's it. Minitab will tell me that Normal 100, the column name, has 100 data points with an average process of minus 0.150, a standard deviation of 1.01, a minimum value of minus 2.47, and a maximum value of 2.292. So if you're the engineer in charge of this, you can immediately know what you're looking for. However, copying and pasting this might not be the fastest way. Let's say I go over to Store Descriptive Statistics and I do the exact same process, but this time I asked to store this information. I'll just click on OK. And if I go over here to the first row, you'll see that I have my mean, standard deviation, minimum, maximum, and number of data points, which is the exact same information I had here. So I can just copy and paste this wherever I want, and I can know immediately what is my process mean, standard deviation, minimum, maximum, without even having to know the formulas from Excel. Now, all of this is all well and good for the engineer. However, when you're doing a presentation, you need to be visual. Managers, general managers, staff managers, even your own supervisor, even if he's an engineer, he likes to look at graphs. That is something that you must understand. People are visual. Even if you understand data points just by looking at them, you need to show them graphs. So the fastest way to create a quick graph would be to go to Basic Statistics, Graphical Summary, just click on Normal 100, then you can leave the confidence level at 95. Most engineers use 95. That is for confidence level that you know that your conclusion is going to be right. We'll be talking about tolerance intervals later on, but for now, just leave it at 95. Just click on OK. And as you can see right here, you'll have a graphical summary with the main data points and the main information that is usually asked when you're analyzing Minitab. So the first thing you have is a histogram, and it's showing you the bell-shaped curve. The next thing you'll have is the Anderson-Darling and the p-value test. So remember what we were talking about if it was normal data or non-normal data? We were saying that for you to be able to have normal data, you need to have a p-value that is higher than 0.05. If I look at my data points right now, they're at 0.014. This means that this data is actually not normal. So I can't actually consider it to be normal. And if I look at the process mean and the process median, they are not actually aligned. What does this mean? If you look at your graph right now, you'll see that the process is skewed toward the left. It's not centered like it should be on a histogram. So whenever your mean and your median are not actually aligned, that means that your process tends to have a shift. It tends to have really high values that turn the mean over to the right, but it has a lot of values that are toward the left. So let's look at this using a normality test like we were doing previously. We're doing a normality test for normal 100. When we execute this, look at the information. The points, the red dots, are not actually following the blue line. They are actually dancing around it. This means that this data is not actually distributing as it normally should. And once again, I look at my p-value. My p-value is less than 0.05. So even if I created this data using Minitab's calculate random data and normal, due to the fact that it's completely random, it took a distribution that is not actually normal. Now, when you start adding additional data points, remember, as you add information, I'm going to be repeating the test, but this time using normal 1000. The data has a higher chance to show you its real distribution. So, once again, just to confirm that it was understood, when you calculate random data, even if you're telling Minitab that you wanted to use a normal distribution, if there are not enough data points, and for some reason the clock, while it was creating the random numbers, created really big values and really small values, you're going to be having non-normal data, even if you asked for normal data. So what's the remedy to this? Well, take more samples. If you have more samples, even if your data is not normal, it will tend to gravitate toward a normal distribution. Okay, so now we're going to be continuing. So you've seen how to create quick graphical information. You've seen how to use stat, basic, display, and store. Now, there are a lot of tests that you can execute using Minitab. We're going to be going back to the slides right now. And as you can see, you can do the same test and you can select what you're looking for. First quartile, median, third quartile, whatever you're looking for. And other than this, you can analyze your data quickly. There's going to be information in the graphical summary that you might not actually be looking for. So if you're not looking for that particular piece of information, you can create your own summaries. Remember, it's very simple. You just run a quick normality test on your data. That could be your first graph. Then you can create a histogram with your data. That can be your second graph so that people know what you're talking about. And your third and final graph, which is actually quite useful, it's called a box plot. So the box plot is very simple. It's pretty easy to understand. What this box plot is telling you, it's a graphical summary of the same information that is right over here. This graph and this graph use the same data, but tell you different things. For example, the histogram tells you how your data tends to be skewed or distributed. So for example, I can look at this and say, this seems to be skewed toward the left. If I look at my box plot tells me where my data tends to be distributed using distances. For example, this point right here, this 10 line, represents the first quartile, and from one point toward its extreme, that represents the first 25% of my data points. So I can conclude that around 25% of my data points fall between -1 and -2.5. Now, if I look at the box is always split in two. There's going to be a line in the middle, not necessarily exactly in the middle, but it will split the top from the bottom. This means this second portion corresponds to the next 25% of the data points. So that means that from this line or to this line, you have 25% of the data points, plus the additional 25% of the data points that you had here. So now you have 50% of the data points. And if you look at the box from the top, from here toward this line, that's the next 25% of the data points. So just by looking at the graph, you can say around 75% of the data points are between 0.5 and -2.5. And lastly, the last tail on the top represents the last 25% of the data points. So this right here from 0.5 over to 2.5 represents the additional 25% data points to make all 100 data points. Now, the importance of the box plot is that it allows you to see non-normal or out of spec or odd data. So let's say, for example, somebody was typing in the information and for some reason they made a typo. So instead of having a 0 or a 0.5, they typed in 500. So, well, let's just do something a little bit smaller. Let's say 10. Okay. Now, I can right click on this graph and just say update graph now. And it will update with the information on column C1, which is the one that it comes from. Now, if I look at the box plot again, the box plot is still the same size, but the scale has changed. That's why it now looks squished. And if I look at this point right here, this is what's known as an outlier symbol. It's something that Minitab is saying this data point is not the same as this information. So let's say I had another out-of-spec data point, and I update graph now. I will have two different asterisk points. So I can hover over them, and it will say outlier symbol row number 2. It has a value equal to 12. So I can look at this right now here, row number 2, a value equal to 12, and I can say, yeah, you're right. This shouldn't be here. And I can also look at the other one that is right here and say, outlier symbol row number 1 has a value of 10. This right here shouldn't be here either. It's not the same as this data, and it's most likely a typo made by an inspector or somebody else on the shop floor. I can right click on the graph again and click on update graph now, and I will have my box plot with the actual information that comes from here. So the box plot can quickly help you figure out if there are data points that are non-normal with the distribution. So for example, let's say you were looking at an analysis of salaries. Let's say you were interviewing people, and for some reason in the United States they were telling you that the average American household made about $300,000. You would say, hey, wait, that doesn't sound right. You make about $50,000, $60,000, so you know that the average can't actually be 6 times your salary. You're not that poor. So let's look at this example right now. Let's say I ask someone in the low scale and he makes about $20,000, and then I ask a few engineers, they make about $50,000, $60,000. There's a very well-paid engineer making $75,000, and let's just put a few other guys around 40, around 50, and a few in 80. Okay? So if I look at the information right here, it doesn't look that far-fetched. But let's say I find an engineer who's also an owner of a software company. So he doesn't make the same money that you make. He makes about $1 million. Okay. And then his golf course buddy makes about $1.5 million. Okay. So when you start analyzing the data, if I just say, oh, let's just look pretty simple, pretty quickly, let's just look from the salary information. I just want to know what the process mean is and how many data points were looked at. So this is what usually happens in the news. When you're looking at news that say, oh, the average salary of the average American is about $319,444. You need to immediately ask yourself, wait, how many data points and what is the standard deviation? Remember, the standard deviation is how much the data points change from the mean over to its minimum and maximum value. So how much each data points differ from one another. So if I say statistics, standard deviation, I click on OK, you'll see that, yeah, the average of the data points contained in C16 for the salary is $319,444. Now, the standard deviation is around $542,474. So that means that we have people making very good money, and then we have people making really bad money. So if I try and graph this using a box plot, and I say, okay, show me the information from salary, I'll immediately see that something is not right. I can look at this right here and say, okay, there's an outlier point, row 9, around 50 million. Oh, I think I mistyped the number. But the example is still the same. So let's say I notice that this is not characteristic with the population, so I just delete it. I can right click on it, update graph now, and I can still see that there's a very big outlier point right over here. So I can say, okay, this guy is also not characteristic with a salary engineer. And I can say right click, update graph now, and now I have a box plot. I can look at it and can say, okay, there seems to be a really big spread between the first 25% of the people. So some people make very little money, just around $40,000, and then most of the people make about $40,000 to $50,000. That's why this box is smaller. And if you look at this part right here, it's a lot bigger. So that means there are a few people that make around $50,000 or $60,000, and then there are a lot of people that make around $80,000. So that pushes up the bar to be a lot longer on this side. Okay, good. So remember, this is a box plot. This is the information that you can get using stat basic displays, descriptive statistics. The information that you can get on your sheet, so you can copy it and paste it on Excel, you'll get it from stat basic store descriptive statistics. And if you just want a quick graphical summary, you can click on it, put in your information, just click on OK, and you'll get a quick histogram. You'll be able to see your confidence intervals, and you'll also see your Anderson square p-value test. So note that this is telling me that my data is actually normal. It has a p-value greater than 0.05, so that means this data is normal. If I would add the information that I had previously again, and ran the same test, I would see immediately that my histogram does not look normal. There's a very big long graph right here, and this bar is telling me, hey, there are a lot of data points around here, but then there are 2 data points that throw the graph off, and if I look at my p-value, it's less than 0.05. Okay? Note that this is 10 times less than 0.05. So Minitab is telling me this data is obviously not normal. Something here is odd and not right. So can erase that, rerun my graph, and I can see right there that this data is normally distributed. Okay, perfect. So let's just go back over to the slides real quick. And And now we're going to be talking about a concept which is basic in all engineering fields, which is called the hypothesis test, which is kind of a mouthful if you think about it. A hypothesis test is just a test where you're saying, is this true or this is not true? Okay, it's pretty simple. So let's say you were comparing salaries from the United States as an engineer over to salaries from, let's say, France. Okay, and let's say we're talking about dollars. So let's say a salary in France is around 30,000 for the first person that you ask, then the next person is around 40,000, and then the next person around 35,000. I keep putting extra zeros, I think. Yeah, I'll be fine. Okay, 50,000, 60,000, okay, and let's go for another 45. And let's say there's a very odd guy making about 80,000. Okay, so the first question that comes to mind is, do people, let's put here salary USA. Okay, do people from USA make more money than people from France by following an engineering profession? So I go to Stat, Basic Statistics, and I have very simple statistical tests that I can execute. The first one is called a one sample C, the next one is called a one sample T, and the next one is called a two sample T. Now I'm going to be talking about each of these hypothesis tests that you can execute very briefly. They're very simple and you should have no issues with them. So the one that we're going to be using right now is called two sample T. Two sample T allows you to compare two samples one against the other. So I can say samples are in different columns. The first column is salary USA, the next column is salary France, and I can use a graph. I can click on graphs and say, hey, give me a box plot of data. I'll click on options just to make sure that my test is a confidence level of 95%. Just leave it how it is. And we'll be clicking on OK. Now, the first thing that I can see right now from my box plot is that seems to be a difference between USA salaries and French salaries. So you can see this line right here. This line connects the process average. And as you can see, people from France seem to be making less money than people from USA. But on the other hand, the spread of the box plot is a lot bigger in the USA. That means that USA tends to have people who make really good money and people who make really bad money, while France seems to have people who make about a minimum that is around 30,000, which is greater than USA's 20,000, but their salaries aren't as high as the American salaries. So, for example, this size right here from 80,000 to around 65,000 is really small, but still, it means that 25% of the data points are around this size. So a lot of people, in our sample of 9 people, around 3 people are making between $75,000 and $80,000. Well, on the other hand, that same amount of people, around 3 people, one is making 80, another is making 70 most likely, another one is making 60. So there's a bigger spread on the people who are making the most money. Now, if I look at my session window, which is this one right here, I'll see that it says two sample t-test and confidence interval, that is what CI means. Salary USA, salary France. Two sample t-test for salary USA versus salary France. It says salary USA has 7 data points, while salary France has also 7 data points. The USA's average salary is around $53,000, while the French salary is around $48,000. So just by looking at this, I could say, hey, USA has a higher average salary. But I can also look at the standard deviation and say, wait a second. The USA has around $20,000 in standard deviation, while France only has $17,000. So even if people from France make less money, their wealth is distributed more equally among them. while in the USA there's a bigger difference between the haves and have-nots. Now, Minitab will execute a test for us. The test will tell us if there's actually a considerable or a statistically significant difference between the USA salary and the French salary. The only thing you need to look at right here is your p-value. Your p-value right now is greater than 0.05. That means that there is not a statistically significant difference between France salaries and USA salaries. Now, just to make sure that that's clear, let's add somebody else. Let's say we'll put a salary in Mexico. So a Mexican salary for an engineer might be around $10,000, and then there might be another engineer making $8,000, then one making $7,000, and then another one making $15,000. Then there might be a really rich guy making $20,000, and another $15,000, and and let's put another guy at $9,000. So if you analyze the data from Salary USA and Salary Mexico using the same tool that we used previously, which is in Stat, Basic Statistics, and 2Sample-T, we're going to put here Salary USA for the first one and Salary Mexico for the next one. We'll make sure that our Boxplot graph is selected, and we're going to click on OK. Now, just by looking at the graph, you can see that the data does not actually match from one population to the other. So for example, if I took the salary from this side, which is Mexico, and tried to move it over toward the left, it wouldn't actually match the data that USA has, which is different than we had from the Salary France and Salary USA. If I grab this data and skewed it toward the left, it would seem to match the same size as the USA data. So that is why Minitab considered the data to be similar, not exact, but not different enough to say that it had a p-value less than 0.05. Now, if I go back to the session window, we'll see 2Sample-T test and confidence interval, Salary USA and Salary Mexico. I'll notice immediately that my means, my process averages, are not the same and not similar. My standard deviations are also not the same and not similar. There's a huge difference between one data and the other. And if I look at my p-value is 0.002, which is a lot less than 0.05. So Minitab is telling me statistically there's enough difference between one data, which is the USA data, and the Mexico data to say that salaries are not the same. So that is how you use a hypothesis test. You can make it for one sample or two samples. Now, the most common that you'll find in the manufacturing floor is 2Sample-T test, usually in the form of supplier 1 and supplier 2. Usually when you're comparing a manufacturing process from one supplier to the other in order to determine which one you're going to pick, you're going to have data from one and the other, and you're just going to run a simple 2Sample-T test to compare their results. Now, on the other hand, let's assume that we only have one supplier, and my supplier is assuring me that his product is at least 15 inches long. Okay? He puts that in his certificate, and that's the information that he supplies to me with each slot. Now, let's say I ask my quality inspector to grab 10 random parts, and the parts are 15, 16, 14, 15, 19, 15, 16, 17, 14, and 13. So I can grab this information right here, and I can do what's called a 1Sample-T test. Now, when I run a 1Sample-T test, I can say, okay, analyze supplier 1. I want to perform a hypothesis test. My supplier is telling me that this is at least or exactly 15 inches long. I can make a graph for the Boxplot data, can do my options. And my alternative is that it's not equal. So what I want to know is this data, the average, equal to 15 or not? You can click on OK, and you can see your information right here. Now, the box plot on the top is the data that I took from my samples. And the box plot on the bottom is where Minitab statistical analysis is stating that the mean of the population, not the samples, but of the population, most likely fits. So the hypothesis mean is that this process will have a mean of 15 units, right? Which is 15 inches long. That's why this HO is right here. And Minitab is telling me that based on the 10 samples that I got and the fact that we don't have that much data, the average of the process is most likely between 16.5 and 14. Since the null hypothesis, which is 15, saying that the process is at least 15 inches long, is inside the confidence interval, the Minitab will tell us that it can't say that it's not. So Minitab is telling us, based on the 10 samples that you got, most likely with a 95% of confidence, I can tell you that the average of the process is 15 inches long. Now, if I look at this right here, my p-value is greater than 0.05. So once again, my graph is giving me the exact same information as Minitab. Now, what would happen if I had more data points? Right now, I only have 10 data points. I'm just going to copy it and paste it. And let's say I kept grabbing samples, and now I had 14, 14, 16, 14, 14, 14, 14, 18, 14, 12, 13, 14, 14. Okay? Now, with this, I have 23 data points right now. 23 data points against the 10 that I originally had. If I run the analysis again using basic statistics, one sample T, erase the supplier side and select the new supplier and run the test. Note what has happened with my confidence interval. My confidence interval has become smaller. As Minitab gets more data, it can be more sure of where the confidence interval lies. So as Minitab gets more data points, it can be more confident that its result is correct. So let's say I got another 10 additional samples, right? So now I'm at 33 samples. And I run the test again. Note what is happening. Originally, Minitab was telling me, yeah, I'm pretty sure that the average of the process family, as in the whole process, not just my samples, but the whole process, is within 15 inches long. But as I've been introducing 14s, Minitab is now saying, hey, wait a second. Maybe the average of the process is not 15, but actually more between 14 and 15, most likely 14.5. Does that make sense? I hope it does. But the point here is, when you're doing a statistical analysis as a quality engineer or a manufacturing engineer, if you're going to analyze two samples between two suppliers, you're going to use a two-sample t-test. If you're going to be analyzing the claim of your supplier that he's telling you that he promises that he meets a certain specification, then you will use a one-sample t-test. Now, there's one last test, and that one's called the one-sample c-test. C as in zebra. So, the test executed by one sample C and one sample T is pretty similar. The only main difference is that one sample T is used when you don't know the standard deviation of your process, but you do know the standard deviation of your samples. And in one sample C, it means that you actually do know the standard deviation of your process. How can you know the standard deviation of your process? It's pretty simple. You will need to have a historical enough data that you have around, let's say your production is about 1 million parts and you have historical data on around 500,000 parts, so that's half your population. So that can be enough to say you know the actual standard deviation of your process. So you can use one sample C. But most of the time you'll be using one sample T since you don't have that many samples, and you need to tell Minitab, hey, I'm not sure the samples that I took are not actually that big when compared to my total lot size. So let's say you took around 50% samples of your lot, then you can say, yeah, I'm pretty sure that I sampled a considerable quantity of the lot. But if you only took about 5% or 10% of the samples of a lot, well, you would use one sample T. Okay? Perfect. So we're going to be going into more detail in further modules about what regression is, what ANOVA is, what design of experiments are. And for now, just keep in mind, Minitab is a very useful tool. You can use it to create random data, remember what normality is, what non-normal data looks like, and what tests you need to execute to say if it's normal or non-normal. We'll be picking it up from here in module number 2, okay? Well, for myself, I would just like to close with a few comments. Let's just go over here to closing thoughts. I would like to thank you for your attention. In case you have any questions, please feel free to reach us out at info@cusum.mx. For further training modules that will be made available about team requests or on comments that you put on the forums. Remember that this is for the CUSUM company. Everything right here is confidential information, property of CUSUM. Its reproduction is prohibited, and for further details, just contact us at info@cusum.mx, and feel free to hit us a like or let us know what you would like us to change, okay? Well, thank you very much for your time. Have a wonderful day. Bye-bye.